Welcome to 31st lecture in the course of Industrial Engineering and Operations Research. We have already delivered 30 lectures related to industrial engineering. Of course, some topics were there that can be considered as part of operations research also, but now remaining lectures will be dedicated to operations research. As we have already discussed that industrial engineering is a broad term, many places there is a branch of industrial engineering in which people can do BTech for 4 years, they study only industrial engineering, and in that operations research is 1 or 2 subjects. Okay. So, that means operations research is a tool that industrial engineers can use. So, since it is a tool, that means other people, there are people in mathematics department, they try to develop algorithms etc. Their focus is not that much in applications, but rather making the algorithms more efficient and developing new algorithms. Those type of things are done. But industrial engineer studies many subjects like electrical engineering, mathematics, material science. Similarly, industrial engineer also studies operations research. So, in the operations research, I will discuss first topic of linear programming. Programming is not meaning here to make computer program, but you can say it is basically the optimization of linear type of problems. Okay. So, programming will be used in that sense. Okay. Of course, to do that task you make a computer program also, there is no doubt about that, but it has to be this one. So, first little bit we will tell what is operations research, in which linear programming is just one part, but in operations research there are many topics. So, LP is one topic. So, first since the word is operations research, so therefore, we have to understand that what is an operation. An operation is some step in the overall process of producing a product or service that leads to the final output. Suppose we are extracting oil from seed. So, there are many operations, there are many activities you can say that collection of seeds, we are collecting the seeds, then we are cleaning those seeds, then we are conditioning those seeds, then we are crushing that seed. So, crushing can be one operation, one operator will be there who will just crush this one, and then we make the extraction of the oil. So, naturally the collection of seeds is one operation, this is somebody else is doing, crushing of the seed is another operation. So, like that we have operations, and one task may need many operations. What is the meaning of research here? Research means we have to understand that operation deeply, and we can see that how we can make it in a better way. Those type of things have to be done. That is what that meaning of operations research. Now, let us just tell some historical perspective of operations research. Sometimes in UK it is also called operational research term, but in USA mostly it is spoken as operations research. Operations research started with World War II, but actually some people say that it was used even in World War I time, and Thomas Edison also did something in that direction, and in fact in one sense operation research, since it is closely linked with the optimization or making the best use of the limited resources. So, its history can be quite old, maybe starting from the calculus time, Newton's time, that this discipline is in existence. But usually the modern concept of operations research started with World War II to optimize the military operations etc. World War II was between 1939 to 1945. So, people wanted to make use of like proper deployment of radar, maybe the proper routing of aircraft with limited number of aircraft, how they will cover various destinations. So, such type of things were done. The term was used by J.F. McCloskey and F.N. Trefethen in 1940 in UK. That is written somewhere, but it is not very authentic information. That's why I have made question mark. Rather, they have written something on the history of operations research. So, in 1952, the Operations Research Society of America came into existence. That this society was made in 1952, and modern operational research at the Bowdesy Research Station in the UK. As I said that in UK it was not called operations research, but it was called operational research. So, it originated at the Bowdesy Research Station in the UK in 1937 as the result of an initiative of the station's superintendent A.P. Roy and Robert Watson Watt. So, this is in UK, and in 1949 Operation Research Unit was established in Regional Research Laboratory at Hyderabad, because India also has been working in this field right from the very beginning. Another group was set up in the Defense Science Laboratory to solve the problems of stores, purchase and planning, like how the material should be procured, how it should be kept. Those type of things were done at Defense Science Laboratory also. So, that time also the techniques were developed. 1953 OR unit was established at Indian Statistical Institute, Kolkata, which is a very premier institute in Kolkata. ISI deals with the statistics, etc. And its purpose was to use operations research in national planning and survey and many other things. 1955 OR Society of India was established, just like in 1952 the Operations Research Society of America was established. So, here in 1955 Operations Research Society of India was established. It is a member of the International Federation of OR Societies. So, this is how that activities have been picking up. So, in 60s etc., 70s etc., it was very hot topic. Now, coming to the definitions of the operations research is the application of the method of science to complex problems in the direction and management of large systems of men, machine, materials and money in industry, business, government and defense. So, you have to understand that we have to optimize men, machines, materials and money, and in anything business, government or defense, the distinctive approach is to develop a scientific model of the system incorporating measurements of factors such as chance and risk with which to predict and compare the outcomes of the alternative decisions, strategies or controls. The purpose is to help management in determining its policy and actions scientifically. So, it provides a scientific framework of everything. So, this is a definition taken from Operations Research Society of UK, and there is another definition. There are several such definitions, but we are just telling you couple of definitions. So, one definition, Committee on OR, National Research Council, USA. This says the application of the scientific method to the study of large complex organizations or activities. It provides top level administrators with a quantitative basis for decisions that will increase the effectiveness of such organizations in carrying out their basic purpose. So, it is also that basically about the optimization application of scientific method. It provides top level administrators with a quantitative basis for decisions. That means you take the decision, but it should not be just based on your intuition or impulse. Rather, there should be quantitative basis that why this has been taken. Is it not? Suppose you have selected some candidate out of 5 candidates. Then quantitative basis means that what are the marks in which areas his strength is there, and that is why it is better than this thing, not just like qualitatively saying that this candidate is better than other 4 candidates. So, operations research generally deals with the optimization. That means you have some objective or goal and you may have some constraint. those things have to be written in the mathematical form. So I would say that perhaps 50% effort should be paid to that, means proper mathematical formulation is not that easy, means we could face the problems, but converting it in the form of mathematics is also very important, but it comes with experience. We do not teach much in academic institutions about that part, only we give some idea, because this mostly comes from experience also. We tell mostly about the method to solve that problem, but the first issue is that how to make a problem. So you have to make mathematical optimization problem is given in this form. It is a general structure, and you can say it is a template. You will solve many optimization problems, but always the form can be like this. So it is that, suppose minimize, let us say it is a multi-objective problem. That means we have got several goals and we have got many design variables, okay, decision variables. That means we have to decide about the values of x1, x2, xn. That is why these are called decision variables, and they are also called design variable, because you can say that we have to design our system based on these things. So we have something that we may have many objectives, okay, like here f1 must be also minimized, it is a function of that. f2 must be also minimized, fp also must be minimized, and this function will be known to us. So that is called objective function. So basically we have objective function. So we have to say, and with objective function we have got constraints. We can say all of them are constraints. That means what is the constraint? Who is stopping you to minimize that quantity? So for that we have got constraints, means they are all inequality constraints. This much is basically up to jm. That means there is a some function, but it should be less than 0. This should be less than 0. It should be this one. So this is called inequality constraint. That means it is not equality, but it is inequality constraints. Let us say we have got m inequality constraints. g1 is another function, g2 is another function, gm is another function. It should be less than or equal to 0. And then we have equality constraint, k equality constraints. So we say equality constraints. That we constraints we have to do that, okay. And then these are also a type of constraint, but mostly people say it variable bounds. That means you have decision variables, so they are bounded. So they are boundaries, okay. xi is less or equal to xi u, means xi upper bound, or we can say that it is xi less or equal to lower bound. So and for I to 1 to n. So this is the any problem you have to write in this type of thing. Now sometimes you may have objective as maximize. So then if it is a maximize also, but you can easily convert into minimize form. You can put the, if you have to maximize something, that means you have to minimize negative of that, or you have to minimize inverse of that. Suppose I have got a function fx, this I have to maximize. So I can minimize minus fx, or I can minimize 1 by fx, okay, whichever is convenient. Similarly, my inequality also, if j1 was greater or equal to 0, then also I can multiply both sides by minus 1, and I can say that it is, I can convert into smaller or equal to 0. So this is not a difficult thing. Even if we have some function, I want to minimize that, then function plus constant is also the same thing. So constant doesn't matter, okay. This is, so some points, okay, that's what I want to highlight this point. If there is only one objective function, the problem is called single objective optimization problem. This problem is what? Multi-objective problem. Because there are many functions you have to optimize, but we have single objective problem. If there are no constraints, the problem is called unconstrained optimization. Sometimes there are no constraint also. We can have, this is called unconstrained. Say for example, somebody says that, suppose somebody has given me function fx and this is equal to x 10 minus x, and he says that you find out the maximum value of this function, okay, x 10 minus x. So there is no constraint, nobody is stopping, I can choose x anything, but I have to tell that yes, at this value of x, this function fx will be maximum. So this is unconstrained optimization. The previous one is constraint optimization problem. So you can say that unconstrained optimization is a special case of constraint optimization problem in which I can put constraints equal to 0. So maximization of a function fx is equivalent to minimization of minus fx. That also I have told. Not only that, instead of minus fx, if you don't want to put minus thing, then you can say okay 1 by fx. That also can be done, and those type of things can also be obtained. Okay. Now, so operations research includes applied scientific methods and techniques to decision making problems for finding out the best or optimal solution. So as I said that there may be constraints, but if that thing by operations research you can solve. And mathematical programming techniques are useful in finding out the minimum of a function of several variables under a prescribed set of constraints. Mathematical programming techniques are useful in finding out the minimum of a function of several variables, and but there are some constraints also. So operations research uses optimization techniques. It also uses optimization technique. So that means it is one part of that, but operations research has many other things also. In fact, proper formulation of the problem is also part of operations research. Then we have topics such as queuing theory, etc. In one way, in a very philosophical way, everything is optimization. But suppose we just have to forecast, we have data for 3 months and we want to predict that what will be in what will be the sale in the 4th month. So based on the 3 data, I am just predicting that. So it is not in a very strict sense it is optimization, because we are not playing with various values and seeing that which is giving me maxima, which is giving me minima. So, but it is a part of operation research. So forecasting is a part of operation research. Okay. Inventory thing, finding out economic order quantity is also part of operation research, but that is basically optimization. So invariably operations research uses optimization techniques. Optimization techniques find application not only in operations research, but in many other areas as well. For example, in finding out the zeros of a function. So similarly, we can't say that both are exactly. So optimization cannot be called a subset of operations research. Similarly, operations research is also not a subset of optimization. If somebody is expert of optimization and he says that I know everything about operations research, that is not correct. Operations research has many other topics also. Similarly, in the optimization, it is we do many other things unrelated to operation research. Say for example, even you want to solve some equation, say if you want to solve say equation x plus y is equal to 5, x minus y is equal to 7. Now this type of problem can also be solved by operation research. So you make some error function and you say x plus y minus 5 square plus x minus y minus 7 square, that much you do, and you find out the values of x and y which make error 0. If you can do that, that means you have got a solution. So that means we have converted these solutions. We can say zeros of a function. Zeros of a function means suppose there is a function, so by taking which value the function will become 0. That means in other words equation solving. So equation solving can be done by optimizing some function also. Such type of things are also studied in optimization method, but not in the operations research. So now let us discuss what are various types of optimization problems. So one thing is the linear programming. Here objective functions and constraints are linear. So linear means that you already know the linear. Say suppose there is some function fx y is equal to say maybe 5x plus 3y. So here that means all the it has got constant coefficient, it has that type of form, and there is no constant term here. Okay, so linear functions have some properties, that means they are if you can say in the linear one, if you know that if suppose let us say that x1 y1 is a solution, and suppose you have got x2 y2 is also a solution, then we can say alpha times x1 plus x2, okay, that will also be a solution. Okay, that means we can have linear combination of that. Okay, that means let us say instead of x1 y1 we say by one number only, x means both x1 and x2. So therefore suppose there is one solution x1, another solution is let us say y1, then alpha times x1 plus, and alpha may be between 0 and 1 minus alpha and y1, that is also a solution. Okay, so they have got certain properties. That means you can say the value of the objective function increases in proportion to the value which you give that. So there is a linear, or you can say that if you differentiate that function with respect to that any variable, you get a rather partial derivative if you take, you get a constant term. So therefore objective function is linear. Similarly the constraints are also linear. Then we have dynamic programming problems. It is determining the optimum solution to an n variable problem by decomposing it into n stages, with each stage consisting of a single variable sub problem. So we can break down into number of stages, that is dynamic programming. But right now all focus is on linear programming. Integer programming is also linear programming, but the variables are integer. That restriction is there that you cannot take other real values, only they have to be integer. And non-linear programming means constraints and all objective functions are non-linear. And goal programming, that means converting multi-objective problems to single goals. Okay, single goal you can say. So this is what this one. So in multi-objective problem, of course, you will get sometimes many solutions in which you cannot offhand say that which solution is better than that. So rather we can say no solution dominates each other. So both are called Pareto solutions. Okay, by both means I mean there may be 10 such solutions, there may be 100 such solutions, but that group is called Pareto optimal solution. So multi-objective optimization problems give rise to a set of optimal solutions known as Pareto optimal solutions, all of which are equally important as far as all objectives are concerned. In a Pareto optimal set, no one solution is better than the other in all respects, that is no one solution dominates the other. An example, suppose we have got 3 students, Ram, Ramesh and Ali. Okay, and their marks in physics and mathematics are given here like this. So suppose he has got 30 and he in physics, and he has got maybe 35 in mathematics, but Ramesh has got 70 in this one physics and maybe that 80 in mathematics, and this fellow has got, Ali has got say 75 in physics, but he has got 77 in mathematics. So in this case, naturally we can say Ram is not a Pareto optimal solution. It is not optimum at all, because Ram has got very low mark. Both Ramesh and Ali are better in both the aspects. Suppose our objective function is what? 2 objective function. I want maximum marks in physics, I want maximum marks in mathematics. So both the things separate. Okay. that type of thing. So naturally Ram is out, but Ramesh and Ali, we are not able to decide. So we can say, suppose I choose Ramesh. So Ramesh is no doubt better in mathematics, but he is not better than Ali in physics. Similarly, Ali is better in physics, but not better than this thing. So these two persons, we cannot decide that who is better. Nobody dominates other in all respects. One is good at one thing, so both are then Pareto optimal solution. Both are Pareto optimal solution, right? But anyway, we will discuss something more about single objective first. So let us say some particular definitions that you know in related to optimization. Usually the objective function is also called cost function. A cost function is that function that is minimized. Okay, so we say cost function. Feasible solutions means all the constraints are satisfied. Any values which may be optimum or not optimum, but it is constraints are satisfied, then it is called feasible solution. Infeasible solution, that means one or more constraints are not satisfied. Combinatorial optimization means finding an optimal object from a finite set of objects, like traveling salesman problem. That means a salesman has to go to 5 cities. Okay, these are the maybe 3, 4, 5. In what sequence he should go, so that overall you know that his distance covered by him is minimized. Okay, should he follow this path or he can follow the other path, he can go from this city. So there are finite number of combinations. Okay, so this is a combinatorial problem. Discrete optimization, values are discrete like integer programming, and of course combinatorial optimization. Now I am going to tell that what is a convex set will come. Suppose a set is convex if every point on the line segment connecting x and y is in C. That means if you have got one point in the set, other point is in the set, then if you join these, then that is also in a set, that is called convex set. And the convex hull of a set of points is the minimal convex set connecting x. Okay, suppose we have got say this zone. Okay, this is the type of straight line type of thing. If we say that these are the constraints, so we can say this is a convex hull because this is a minimal set. Of course, if we make the set like this also, then also that property will be there, that if something is here and something is here, and if you join, that is also in the constraint, but that is not the minimal convex set, means this one. And non-convex set is this type of thing, that here see one point is here, one point is here, but if you join that, many points will be outside the set. So now coming to the linear programming problem, suppose I give one example to formulate. Suppose product M1 requires 1 kg R1 and 2 kg R2. 1 unit of M2 requires 3 kg R1 and 1 kg R2. Maximum available R1 is 100 kg and maximum available R2 is 150 kg. Then profit of M1 is rupees 2 per unit and that of M2 is rupees 3 per unit. Formulate the problem. How you will go? First you make the objective function. We want maximum profit. So maximize 2M1 plus 3M2. M1, M2 becomes the decision variable. Suppose here M1 is also, it is a product name also, but here you consider as the quantity of that product. So 2M1 plus 3M2. Subject to what is the constraint? Because you have one resource you need to make that is 100 kg only. So this is less or equal to 100. What? Because if you make 1 unit of M1, you need 1 kg of that resource. So 1 into M1 plus 3 kg of and 2 kg of R2. Okay, this is you have got 100. So 1 unit of maximum available is 100 and product M1 requires 1 kg and 2 kg. So therefore it is basically 2 kg of requires 1 kg and it needs 2 kg 1 unit. So this is 2 kg, but M2 requires 3 kg R1. So M1 plus 3M2 is smaller than 100. And about the resource 2, 2M1 plus M2 is smaller or equal to 150 and M1, M2 is of course greater than 0 because quantities cannot be negative. So this is the type of that type of problem. And then similarly we can have other type of similar type of problem. We can have many things. Say factory produces 3 products P1, P2, P3. Now let the production quantity of these products be the design variable. X1 is number of units of P1, x2 is this one. So we can have objective function. Suppose we know the profit per, so first you make the objective function, and suppose so z is equal to 30 times x1, 20 times x2 plus 40 times x3. Then you put the constraints. Suppose you have constraint on machine time. Each product requires some machine time. P1 needs 2 hours to make 1 unit, P2 needs 2 hours, and total time is 100 hours. So 2x1 plus x2 plus 3x3 is smaller than 100. Then labor availability may be there. You must use the labor actually, so that people should not sit idle. So that can be greater than constraints. To maintain balance in the inventory, number of units of P1 must equal to P3. If that type of thing is there, then put x1, x2, x3, and then non-negativity constraint are there. So those type of constraints can be put, and this is how that we can formulate a linear programming problem. Maximum market demand, we can say x1 may be less than 40, x2 may be less than this one. So then we make the complete, that linear program here. So we will understand more such type of things in the later classes, but that in the standard form a linear program is written like this: minimize this is equal to this, and we have only equality type of constraints. So if there is inequality, then what we can do? We can add some additional variables. Those are called strike or surplus variables that we will be discussing. Okay, so this will be, so basically in the compact form, minimize CTX subject to AX is equal to B, X greater or equal to 0, and we can use strike or surplus variables for converting inequality into equalities. So we can define, okay, free variables can be expressed as the difference of two non-negative variables, because in standard form I want that x should be greater or equal to 0. So therefore what happens, that if I have no restriction, I can express that particular thing as x plus minus x minus. That means it can be considered as the difference of two positive quantities. That means any negative number can be represented as this one, difference of two positive quantities, and then we can say put a restriction that x plus and x minus both are greater or equal to 0. That way we can do that. Now what is basic solution? Consider a linear programming problem consisting of n decision variables and m equality constraints. A solution obtained after making n minus m variables 0 is called basic solution. Suppose we just put n minus m variables to 0 and solve for the remaining, then that is called basic solutions. And basic variables, if there are m equality constraints in a linear programming problem having n decision variables, then we can assign 0 values to n minus m variables and solve the m equations for remaining m variables. These remaining m variables are called basic variables. Okay, so these concepts of basic variables etc. are there, which will be useful, and we will continue in the next lecture. Okay, thank you very much.